buckling or eccentric loading. Okay. So the thing to take note is these two terms over here. One is called centric loading. It means the load is acting on the centroid, and the other one is eccentric. Right? You can see an offset. The load P has an offset from the centroid. Okay, and it will also, if the condition is right, buckling will also occur. Okay, and buckling will never occur if the structure is loaded this way. Okay, if you see any structure loaded this way, if you see structure, so again, this is our centroid. Now the structure, the load is applied in the opposite direction now. Okay. So when P is acting or is inducing tensile load, okay, failure due to buckling will not occur. So if you see the structure under tensile loading, so do not consider buckling at all. Okay. The failure mode is no more by buckling. It can follow due to stress equal to force divided by area. Okay, so that's how it's going to fail. Right. Question from anyone regarding this matter? So far, it's very straightforward. Only compressive loading can induce buckling. Okay. Now the next thing that I want to take note is I want you to recall something that you have learned before under axial loading. Okay. So the next thing I'm going to focus on is how does mechanical properties relate to the stiffness of a structure. Why I highlight the word stiffness, usually the term used is when the structure is stiff, buckling will not occur. Okay, so I'm going to see, okay, we just use the word stiff, right? All right, so I'm going to tell you or explain what is the term stiffness relate to buckling or relate to material deformation under axial loading. Right. So if we have a structure, let's look at a condition under axial loading. Okay, under axial loading. So now we have a structure that is built in, and then this is our beam. This is our beam. And again, the beam has a centroid. And the beam having a centroid I'm going to focus on pushing the load in. Okay. And then we have this specific dimension. So this is your L0. Okay. So I do apologize, I should not draw P down here. So we basically have a structure that's no load. And over here, this is your AS. Okay, AS is the cross-sectional area. And the next one, what we're going to do is we're going to put a load. Before I put any loads, I'm going to have drawn our transformation. So this is X and this is Y. And now the same structure again. We're going to put a load. And then when we put a load, okay, there will be a change in length. And this is exaggerated. Okay, by right, it's not so much. Okay, but I want you to visualize, see it. Again, this is our centroid. And now we have a load pushing in. And you realize that the length is shorter and this is our EY. Okay. So now the length becomes smaller. So this is our L1. And if I were to extend the line, the original length, over here is what we have as our delta L. Okay. So now looking at the formulation now, we know that the normal stress in the y direction is equal to minus P over AS. Okay. So we have stress Y. So let me define stress Y is the normal stress acting in the Y direction. Then we have Py, which is the load acting in the Y direction. And we have AF. Again, we know that this is cross-sectional area. Right? Because the load is under compression, we have a minus sign. Okay. And then the next thing that I like to highlight is epsilon is equal to delta L over L naught. And this will be equal to L1 minus L naught over L naught. Okay. Where epsilon is the normal strain. And we know delta L, L naught, and L1, they are all shown down here. Okay, we know that this is L naught, L1, delta 1. And I'm going to put units into all this. Strain has no units. Cross-sectional area is in meters squared or inches squared. Py is in Newton or can be pound force. And the stress is in Pascal, or over here, it can be pound per square inch, okay, PSI. So what we realized over here, right, we know note under compression, right? L naught is greater than L1 or L1, right? L naught is greater than L1. Therefore, epsilon is equal to what? Negative. Okay? Your epsilon has to be equal to what? Negative. Because L naught is greater than L1. So why am I emphasizing on this? So now if we were to construct stress strain curve, right? If we were to construct stress strain curve, we know on a stress strain curve, one of the axes is for normal stress, and the other axis, sorry, this is for strain, and the other one is for stress. Okay, so this is for epsilon, this is for sigma. Okay, and we know because our strain, right, is in negative, and our stress is also negative. So the stress strain curve we will get in the elastic region will look like this. Okay. Why is that? Because over here is where stress y is negative, and over this side is where strain in the y direction is also equal to what? Negative. So this gradient over here is equal to our E, and E correspond to our Young's modulus. Okay, it corresponds to our Young's modulus, right? So we are going to form, we already formed two equations. Okay, so we know that this is our equation number one. Okay, we have our equation number one. Hold on, someone have typed something on the chat, and I want to see what is it. Oh, okay, nothing. So I'm going to call this equation number one. Over here, we are going to call this equation number two. Okay. So we are going to apply. Okay, we're going to substitute equations 1 and 2 into Hooke's law. Okay, where Hooke's law specifies that stress y is equal to Young's modulus multiplied by epsilon y. Okay, so can you put equation 2 down here? There's a y, please. Okay. So we're going to substitute equation 1 and 2 into Hooke's law, and Hooke's law is this law over here. So we know that stress y is equal to minus Ey over A, or force in the y direction divided by A. And this will be equal to Young's modulus, okay? And epsilon y will be equal to minus delta y over L naught, okay? So the change in length, delta y or delta L, is equal to Py L naught over AE. Okay, so this is our equation 4. And for this case, okay, delta L